Electron group shape, molecular shape. This ought to tell us. So, what did we consider first? 2 electron groups. All right, and what were some of the examples we had here? HCN was one of the examples. CO2 was one of the examples. We have 2 electron groups. And that was a linear shape.
Can you, sorry, please, if you don't mind, can you like write down the electron group? Because I'm trying to picture in my mind what you're talking about, but I can't remember.
I don't know what the question is.
What was the compound that you just said?
CO2.
Okay, so HCN was one example, CO2 is another example. Okay? And I don't think we'd ever have lone pairs of electrons, and so the molecule is going to be linear. So both of these examples are linear in shape. And then with 3 electron groups, we had planar triangle. And if we had 0 lone pairs, then it was planar triangle. If we had 1 electron pair, right, then the structure would be bent. What if we had 2 electron pairs? I guess it'd just be linear. I don't know of any examples like that, but if you had Y and X and 2 electron pairs, then with only 2 atoms, you can only have a linear shape. So with 4 electron pairs, it's tetrahedral with no lone pairs. It's tetrahedral with 1 lone pair. It was triangular pyramid. Here, with 2, it was bent. With 3, linear. And there's an example for each.
Could you give us an example, and could we like use a chart to figure out what it is?
Okay. How about we try the nitrate ion? Are we doing this together? So, valence electrons. Nitrogen,
5,
oxygen, 6, but there's 3 of them.
18,
18. Negative charge,
1,
1. Total, 24. Central atom.
Nitrogen.
Sounds like a plan. Next step.
Found the
Next
oxygen.
outer.
Outer guys with single bond. Okay.
Track those.
How many have I used?
6,
6,
18,
18. So what's the next step?
Outer bonds, or outer.
Do fill up the hour.
Do the text for the outer guys?
Yeah.
So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. How many do I have left?
0.
0. Are all the oxygens octetized?
No.
Yes.
Yes.
Is the nitrogen octetized?
No.
So I don't have any more electrons, therefore, like so. So now I have the correct dot structure. So my central atom, how many electron groups do I have? 3. So I'm dealing with 3 electron groups. The electron group shape is planar triangle. And how many of those 3 positions have atoms in there? Or how many lone pairs of electrons do I have? I have 3 atoms that are bonded. I have no lone pairs. So with no lone pairs, the shape stays the same, planar triangle.
How do you determine the lone pair?
Well, I would look and see it like this. Remember, lone pair is a
Okay.
non-bonding pair of electrons.
Okay.
So it doesn't have them.
And it has 3 electron groups because there's 3 oxygens.
1, 2, 3. Not because of 3 oxygens, but because around the central atom there are 3 clusters of electrons.
Okay.
If it had the lone pair, it would be trigonal pyramid. Because with a lone pair, there would have been 4 electron groups, tetrahedral. With 1 lone pair, I get trigonal pyramid. Okay? We're there? Of course we are.
Can you do it with a lone pair?
Sure.
I mean, yeah.
Let's try NF3. How many valence electrons? Nitrogen. Fluorine. 7, but there's 3 of them. 21. Total? 26. Central atom?
And
Single bond to each of the fluorines. How many did I use? Got 20 left. What do I do? Build the octets around the fluorines. How many did I use?
80.
How many are left?
2.
Put them around the nitrogen. Are all the fluorines octetized? Nitrogen?
Yes.
Half campered? So, electron group shape, tetrahedral, because there's 4 electron groups. 3 of them are bonds, 1 of them is a lone pair.
but you have 1 lone pair, so wouldn't it be triangular pyramid?
Well, the molecular shape would be.
How did you,
Oh, okay.
it was
I have 4 electron
Oh,
groups.
that's long.
oh,
4 electron groups tells me that the group shape is tetrahedral. If I have 1 lone pair in there, then the result is triangular pyramid.
Mm. It's not as straightforward as you thought.
I'm so glad I asked that.
Triangular pyramid for the molecular shape. It's tetrahedral for the electron group shape. We're talking 2 different things here.
it's not triangular.
And why is it tetrahedral for the electron group shape? There's 4 of them. So 4 gives you tetrahedral.
I told you to do that.
Okay.
Yes, sir.
Is there a tetrahedral with 4 lone pairs?
That would be an atom. That would be a noble gas atom. And it would just be a point. There would be no shape to it other than one single atom. So,
Wasn't the molecular shape you put out? The last.
triangular pyramid. All right, we're ready to go back to polar and non-polar? Yeah, because we love it, right? Let's go back and do a little quick review. If I have 2 chlorines, how many valence electrons chlorine have? 7. So 1, 2, 3, 4, 5, 6, 7. If I bring another chlorine into the picture, how many valence electrons would it have? 7. So I'm going to pair him up here. 1, 2, 3, 4, 5, 6, 7. And I've created what we would call a covalent bond between these guys. The covalent bond in this case is perfectly covalent because each of the atoms are identical, which means they have to have the same electronegativity, which means they're both attracting the electrons in the bond to the same degree, which means they're sharing perfectly. So this is a perfectly covalent bond.
Would that make it polar?
Non-polar.
Non-polar, right?
So that would make it nonpolar. Nonpolar means that it's not perfectly covalent, that there is an unequal sharing taking place. So the way I'm going to get that is to again take a chlorine, but this time I'll pair it up with a fluorine. And the picture shows that they're sharing the electrons, and so it's a covalent bond, but they are not sharing perfectly. Why? They're not the same. And if they're different, one of them has a stronger attraction for the electrons than the other. Is there a way I could tell which one does? It's fluorine, because it has the greater electronegativity. Not mass, electronegativity. And how do I know that? There's a trend in the table that tells me electronegativity from top to bottom decreases, left to right increases. So fluorine has got to be over chlorine. So this is a covalent bond in general terms, but we would use the word polar covalent to indicate that the sharing is not equal. And that means the bond is polar. And we would represent that with a little arrow device that always points towards the negative, and we put a little positive tail on it so that we show the positive guy. Well, what do you mean by stronger? Stronger attractor of the electrons in the bond? Yes. Because if he's a stronger attractor for the electrons in the bond, then the electrons hang closer to him, and electrons are negative. And so he's going to have the more negative charge. Is that a question or a... Okay, good. Yes?
Does it matter if you put fluorine first?
You mean on the left?
Yeah.
No. The people on the other side of this board are seeing that exact picture. All right? They're looking at it and they're seeing the fluorine on their left instead of on your left. Sure, I'm going to put it from the positive guy to the negative guy. In either case.
Can we do another one?
Sure.
Did you get the email?
You get a heater?
Yeah.
All right, how about you try HCl? Give you 12 seconds to map out the dot structure and decide what side is positive, what side is negative, if there is a positive negative side, or is it polar or nonpolar? Such a cute little pencil that you have. Is it?
I'm pretty sure because hydrogen.
Let's pretend it's polar covalent. Why not? Is the hydrogen not happy?
It would be polar.
It might say on it.
Well, let's say it's not in this case. Let's just say it's polar. And what do you come up with?
It's not equally shared, so
It's perfect.
it's polar.
Okay? So conclusion should be, I don't think so. The only time we would say perfectly covalent is if the two atoms were
The same.
exactly the same. H is quite different than Cl. So it's polar covalent. Which way does the thing point? Yeah. That's a little hard to tell because hydrogen's an exception to all of our trends and rules
I was
usually.
about to say, how come?
So, but chlorine is a pretty powerful electronegative element, so our gut feeling would probably tell us that was the case. Okay? Well, you can look at it probably either way, because in solution it is going to actually transfer and give. But for this exercise, we could view it as a polar covalent bond. Yeah.
So being that we don't, so do the trends apply to hydrogen?
Say it again.
The trends like.
The trends generally don't apply to hydrogen real well.
So would you not put one of them in the case like a hot something? That
I would not. I would never think to do that.
So you wouldn't ask us if this was a covalent? Or,
I'd probably pick a better example for that.
okay.
Okay, now, in truth, most bonds are polar. Okay? And in fact, what we can do is we could view ionic bonds as being an extreme of polar. In other words, what are we saying? Polar is, in your own words, what's polar? Unequal sharing of the electrons. If somebody gave their electron away, would that be a pretty much unequal sharing of electrons? Pretty much so, right? So what we're talking about are degrees or extremes here. If something gets to be very, very polar, then we would expect to maybe call it ionic. So maybe we could view it like this. Here is the spectrum of polarity. And right here is perfectly covalent. And can I have that situation? Yes. If I have two identical atoms, I know I have that situation. But as soon as I step off that line of being perfectly covalent, what am I?
Polar.
I'm polar. Okay? But am I very polar if I'm right here? No. So I would describe this by writing it this way. All right? Get the idea? The further away I am from having the same electronegativity, the more polar it's going to be. Now, somewhere over here, I'm likely to call this, maybe not polar anymore, but call it ionic. Let me give you an example. I bring in a beaker, big beaker of ice water. And we ask a student volunteer to come up and stick their hand in the ice water for 10 minutes. At the end of 10 minutes, we ask them, how does it feel? And what do they say?
Polar.
No.
Okay, now, before it gets numb, what are they going to say?
Cold.
Cold! This is cold water. Okay, good. We get another student to come up, and I have a beaker of water sitting on a hot plate that's boiling. And we ask them to stick their hand in there for 10 minutes. And at the end of 10 minutes, we say, how does it feel? What do they say? Hot! This water is hot! Okay, third student. I put the ice water on the hot plate. And I ask the student to put their hand in there, and every minute, we're going to ask them, how does it feel? What's their first response going to be?
Cold.
Cold. Second one.
Warm.
Okay, cool, lukewarm. Third response. Warmer. Maybe nice. Fourth, fifth, sixth response. Hotter. At some point, they're going to say, this is hot, right? It's no longer warm, it's hot. Tell me the temperature where that happens.
Boiling?
It's going to take boiling for you to say hot?
No.
I don't think so. Okay. I don't think we can say, because isn't it going to be different for other people? Some of us are what? True weenies. We put it in our hand 10 degrees above room temperature, we're saying, whoa, this is hot. Others come in the room and say, oh, this is cold, you know. So it's not the same for everybody. So that's the kind of situation we're up against. Where does polar change to ionic? I don't know. I just kind of have a feel for it, right? It's kind of like hot versus warm water. The better question is, if I were given two examples, could I declare which one was more ionic or more polar than the other? So if I had oxygen fluorine and boron fluorine to compare, both of those bonds are polar. Both of them are polar. Why? They're not the same. So my immediate response is going to be polar. Okay, is one more polar than the other? Which one would I label with the higher polarity?
The one with the greater difference in
The one
electrons.
with the greater difference in electronegativity. And what would that be here? Well, based upon their positions in the periodic table, oxygen and fluorine are right next door to each other. They must have a pretty close value in electronegativity. Different, therefore polar, but not very much. But boron and fluorine, that's got to be a bigger difference in electronegativity. So they have to be the one that's more polar. So that's probably the type of question that could be asked. Which of the following is the most polar? Or which of the following is the most ionic? That's not to say they're ionic, but which one shows the most ionic character? Because polar is a form of ionic character. So we would say BF is the most ionic. And that does not necessarily confirm that it is ionic. It's just saying that it has the most ionic character. Yes, sir.
Yes, yesterday, the last class, you said sodium chloride is ionic.
I did.
You said hydrogen and chloride. Maybe the same thing.
Well, maybe not.
Sodium gave electrons.
Right.
Chloride and hydrogen.
Maybe not. Maybe the hydrogen doesn't give the electron. The hydrogen can share. Okay, what's going to make that difference? Probably the electronegativity values. All right, who's got a textbook can look up the table of electronegativity. I've got one here. The electronegativity value for chlorine is, let's say, 3.0. That for sodium is 0.9. All right? 0.9 versus 3.0. Is that a big difference in electronegativity? That's pretty big. We would probably go with ionic. Now, let's talk about the hydrogen. Hydrogen's value is 2.5 versus 3.0. Is that a big difference in electronegativity? I don't think a big one. So I think we're probably more correct in calling that a polar covalent bond than we are calling it ionic, if we look at the actual numbers. Now, to do that, I had to look at the actual numbers. You're absolutely right. If you look at the periodic table, you're thinking, oh, that hydrogen, he's got to be a low dude on the electronegativity scale. But hydrogen's an exception to just about everything we do. So we have to treat him with kid gloves, you know the type, you know. Take special care with that particular gun. All right. Are we understanding? A little bit. Good, then let's complicate the issue. It's what we do. Okay. Now, I'm talking about a bond being polar or nonpolar. What I want to get to is talking about the molecule being polar or nonpolar. And that's a different issue. It's the same issue in the sense that the definition of polarity is the same. Are the electrons distributed evenly throughout the molecule? Okay? Are the electrons distributed evenly throughout the bond? We've been focusing on the bond. I want to focus now on the molecule. And so, how do we tell if a molecule is polar or nonpolar? It takes two tests to decide. Test number one, are the bonds polar or are the bonds nonpolar? If a molecule has only nonpolar bonds, then the molecule has to be nonpolar. If the molecule has only nonpolar bonds, then the molecule is nonpolar. This makes sense. Think about it. What we're saying is if the bonds have an even distribution of electrons, will the molecule have an even distribution of electrons? Very likely. So if it's a nonpolar bond only, then it's a nonpolar molecule. That's the easy case. All right, case 2. What am I waiting for? These are deciding whether the molecule is polar or nonpolar. So, case 2. If the bonds are polar, now I have to consider the geometry. Okay, I have to look at the shape. Because what we're saying is, you could have polar bonds, but if they're arranged in such a way, they might cancel each other. Now, the best way to think of this is perhaps a tug of war, okay? If I have one of your chairs up here, it's on wheels. If I pull on the chair, will it move? Yes. All right, if the chair moves, that's considered to be polar. So if I tie a rope on the chair and pull in this direction, will the chair move? That's a single bond. It's an H and a Cl. That's a polar molecule. If I have only one bond, then whatever the bond is, that's what the molecule is. So if we said HCl was a polar bond, then it's also a polar molecule because there's only one bond there. If ClF is a polar bond, it's a polar molecule. Cl2, nonpolar bond, nonpolar molecule. Now what if we get to a more difficult example? Let me give you this example. Carbon dioxide. Does anybody remember what our dot picture for carbon dioxide looked like? It was a double bond thing, right? Looked like this. How many electron groups are on the central atom?
2.
Therefore, the shape is linear. They're perfectly opposed to each other. So, if I tie my rope onto that chair and pull in this direction, but my identical twin comes in and ties his rope to the chair and pulls exactly opposite from me, are there forces at work on the chair? Will the chair move? Why? Those forces are exactly opposite each other and they cancel each other out. And so the molecule is nonpolar. Even though it's got polar bonds, because of the shape of the molecule, it's nonpolar. If I have polar bonds, if I have nonpolar bonds, it's not an issue, right? If I have only nonpolar bonds, what's my conclusion? Nonpolar molecule. If I have polar bonds, I've got an issue. I have to say, well, what's the shape of the molecule? If the shape is such that I'm going to directly oppose another force with equal power, then they're going to cancel and the molecule will be nonpolar. Okay? Now, let's contrast that with this guy. Who remembers what the shape of water was? It was bent. We probably don't have to go through the whole structure, but it's bent. Okay? That's a different shape, a different geometry. Now, if I tie my rope onto the chair and I pull in this direction, and my identical twin ties his rope but pulls out toward you, not opposite me, but out toward you, will the chair move when we pull? Yes, it will. You don't think so? It's like a slingshot, yeah. I'm going to be pulling in this direction, he's pulling in that direction. You see, those forces don't oppose each other, so there's going to be a net effect on the chair and it's going to move. This is a polar molecule. The shape of this molecule has allowed it to be polar.
So it only becomes non-polar when it's linear?
Au contraire. What if I had CH4? Remember what the shape of this was? It was tetrahedral, okay? But every one of these angles here are all the same. They're all identical. So if I tied my rope onto the chair, let's flatten it out into 2 dimensions to make it a little easier to see. I tie my rope onto the chair this way. My twin ties his rope and pulls exactly opposite from me. Our triplet ties his rope and pulls toward the class. And our quadruplet ties his rope and pulls toward the blackboard. We all pull at the same time with exactly the same strength. Does the chair move?
No.
Perfect cancellation, it's a nonpolar molecule.
So, wait a minute,
So it's basically if it doesn't move, it's non-polar.
Basically, if it doesn't move, it's nonpolar. That's exactly what we're doing. This is the tug of war method. Okay?
I can do that. That's,
You said water is polar because it moves,
Yeah,
and that one's not polar because it's going,
because it won't move.
it's wrong.
That's what I'm saying.
So what about that one, the three? Would that be, non-polar?
This is the one we just did.
Oh, I didn't see the word, but what if it's like three? What if it's three and they all pulling?
Excellent question. What if I have 3? Okay? Now, what if those 3 were in a planar triangle position? Okay? These are perfectly equal angles, 120 degrees each. So, I tie my rope here, pull this way. My twin is pulling at 120 degrees, and our triplet is pulling at 120 degrees that way. It's not going to move. We got perfect symmetry here, right? Perfect cancellation, nonpolar. Now, what if it were the case where it's trigonal pyramid? The nitrogen is here, the chlorines are in a perfect triangle down here, and they're pulling on the nitrogen. Think about a helium balloon in the Thanksgiving Day parade. If 3 of those guys are pulling down, will the balloon come down? Polar.
So when you don't have any loner pairs, it's non-polar, but when you have loner pairs.
Don't make up your own rules. Okay? You're going to be in trouble if you make up your own rules. You are looking at the molecular shape and asking, do those bonds cancel? It's immaterial with lone pairs. Okay?
But there's a pattern.
You're drawing the wrong conclusion if you're going to do that.
So I have a question. So the difference in between the 2 triangles, the even one is a planar triangle and the non-even one is the pyramid?
Yes.
Triangular pyramid?
Yes, those are different geometric shapes.
Okay.
And so they will result in a different tug of war result. Okay? Now, how about HCN? That was one of our examples of a linear molecule. It looks like this. Linear. What's our guess?
Yeah.
Okay, so what you're saying is if I have a chair here, and I tie my rope on this side and pull this way, and Arnold Schwarzenegger ties his rope on that side and pulls that way, will the chair move?
yes, it will.
You don't have to say which way it moves, but will the chair move? Then it's polar.
Yes.
Because now what? They're opposite forces, but they are not equal opposite forces. So there's not cancellation. So that's going to be a polar molecule.
Does the electromagneticity affect this?
Absolutely. If you've got 2 atoms that have exactly the same electronegativity, then the bond is going to be nonpolar, and the molecule will be nonpolar if that's the only bond there. Okay? Now, this description that I've given you is what I call the tug of war method. Works great. You understand tug of wars and you understand the chair moving and so forth. There is another way to view this. And if you're more mathematically minded, you might like this other way. If you don't like the other way, yeah, la, 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 la. Cover up your ears. But if you do, maybe it'll help. Okay, what we're going to do, we'll look at HCl first, is we're going to look at the bonds and ask this question. Is the bond polar or nonpolar?
Which one are we looking at?
Why polar? Because it's an H and a Cl. It's that easy. If they're not the same, the answer is polar. Okay, tougher question. And you've already answered it, so you should be able to get this from this. Which one of them is more negative? The chlorine. So, here's what I want to do. I want to look at this molecule and say, can I draw a blue dot that represents the one point that would be the center of negative charge? where would I draw that dot? Or perhaps in the middle of the CL, right? This is the center of negative charge. Now with the red marker, I'm going to draw the one dot that is the center of positive charge. Where would I draw that dot? In the H. If those two dots coincide, well, what does that mean? If they are in exactly the same position in space as each other, the molecule will be nonpolar. Do these two dots coincide? No. This is polar. Do another example. Okay. Carbon dioxide. Bond at a time. CO, polar or nonpolar? Polar. Which one's more negative? The oxygen, right? So there's a negative charge there, and that means there's a positive charge here. All right? Let's do the other bond right away. Oh, it's a CO bond. Polar or nonpolar? Yeah, you get a different answer here, you're in trouble.
Polar.
Which one's more negative? The oxygen. So there's a partial negative charge here. Now, if I have to draw one red dot that shows the center of positive charge, where am I drawing it?
Middle of the C.
Middle of the C. Now, don't answer yet, but I'm going to ask you next, if I can draw one blue dot that is the center of negative charge, where would I draw it? But don't answer. First, we're going to go out to recess. So we go outside and we're playing on the seesaw. And we got Frank here and Francis here. And Frank and Francis happen to weigh exactly the same weight. So when I put them on the seesaw, this is what it looks like, right? Now, if you had to pick one point that was called the center of mass here, where would you pick that point? Right there. Even though most of the mass is not there? Most of the mass are on the two ends, right? But the center of mass would be in the center. Okay, recess is over. Back to class. I need one point that is the center of negative charge. Do those 2 points coincide?
Yes.
Non-polar.
Okay.
Non-polar. Okay? So if you like charges better, and this works for you, so be it. If you like tug of wars better, and that works for you, so be it. But you're likely to be asked about polar and nonpolar molecules. Yes, ma'am.
So the molecule, we won't need the line to show which the rank stands for. I mean, is the dot the replacement of the.
Yeah. And you don't have to draw this if you don't want to, most likely. As long as you can figure out that, okay, it's polar, therefore I've got a rope on it that's going to be pulling in one direction or the other, then that'll work for you. Okay. Now, these covalently bonded compounds tend to make a different kind of substance overall. They make what we call molecular substances. We talked about ionic substances, and what did we talk about ionic substances? They had certain properties. How many people looked at some salt? What a pitiful class. Okay. I did. What a pitiful instructor. All right. Try to look at a piece of salt. We find that crystal lattice, right? And we find that it's too small. You're young. You've got good eyes. I've got old eyes. I can't see it, and I can still see that beautiful crystal structure. Why don't they? Actually, we can. If you look at rock salt, you'll see bigger examples of it. So buy a bag of rock salt and take a look. And in fact, if you find some irregular pieces, you can actually take a razor blade and what we call cleave the salt off into some beautifully smooth sides. You can make perfect little cubes that are maybe so big, so forth. I've done it. Yeah. Okay, so molecular substances tend to have different properties. Ionic substances had very high melting points and boiling points. Didn't we say you couldn't melt salt on your stove at home? You can't. Okay, did you try it? All right. You can't do it. All right? But molecular substances tend to have much lower melting points and boiling points. So what are some typical molecular substances? Water. Water is a molecular substance, and it melts at 0 degrees centigrade, boils at 100 degrees centigrade. Okay? Methane, CH4, this thing right here, is a molecular substance. And that means that these things exist in individual molecules, not crystal lattices, but individual molecules that really want nothing to do with the next guy. Okay? And so these guys at room temperature exist as a gas. You know that because in the coldest of winters, that gas comes through the pipes and feeds your furnace and keeps you warm. Okay? If it liquefied out there in the street, then it would never make it into the house. And you'd have a very cold type of winter. Now, when we name these things, we also sometimes name them a little bit differently. We will use what are called Greek prefixes. For example, everybody knows the name of this substance right here. It is carbon dioxide. The di is a Greek prefix that means 2. When we use Greek prefixes, what the Greek prefixes do is exactly what I told you the Roman numerals do not do. What did I tell you about the Roman numerals? The Roman numeral is a charge on the metal ion. It is not the number in the formula. Okay? A Greek prefix is the number in the formula. It tells you right off the bat how many atoms there are. So carbon dioxide means literally C and 2 oxygens, O2. What would carbon monoxide be? CO. What would dinitrogen pentoxide N2O5? Okay. So Greek prefixes are sometimes used. Now, here's the deal. They're not used all the time. And so to keep things straight and easy for us, you want easy? Here's the ground rule. You may not use Greek prefixes unless you have permission.
Are you going to give us permission?
Yes. If the problem says use Greek prefixes, then you should use Greek prefixes. If it doesn't say that, then you shouldn't. All right? So in other words, never mind. FeCl2 is what?
Iron 2.
You were not given permission to use Greek prefixes. Do not do that. This must use the Roman numeral. So this is iron 2 chloride. All right. You may use Greek prefixes.
Sulfur dioxide.
Lord help us. Sulfur dioxide. Okay. Now, I will use Greek prefixes. So if I gave you a test question that said dinitrogen pentoxide, then you could write N2O5. Can I make what? Majority of the test? Absolutely. 105 points. Yeah, I expect it. All right. Questions? Sir?
The name of the prefixes doesn't now only apply to non-metal.
Pretty much it does. And often with just, not always, but often with just oxygens. So it's a good rule of thumb. But again, that alone is not giving you permission to use them. You have to be told you can use them on a test before you can use them. Okay? So here's one that doesn't use oxygen. Carbon disulfide. What's the formula?
CO2.
Carbon disulfide.
CS2.
Say it with pride. All right, CS2. Carbon disulfide. All right, I want to make sure that you have the trends down, so I prepared a little handout sheet for you to practice some trend problems.
Yeah.
Don't call her. I didn't think that. I was doing my mouth. I'm doing my mouth. I haven't said today. I was being honest. I'm just kidding. Where's your
Which has the largest ISA?
All right, so I think we've covered everything that's on the next exam. So the question before us is, when should we have the next exam?
Next Thursday.
Now, keep in mind, next Tuesday, I'm giving you the day off so you can study. No, you can thank me, it's all right. So next Tuesday is the 15th, so you're talking Thursday,
The 17th.
the 17th.
No.
Okay. We're not having a review day, are we?
Any other nominations?
Well, if we have
All right, before you vote, keep in mind that if it's this day, we are going on to chapter 5 on this day.
No questions?
I'll answer some questions, but I'm not going to answer questions for 75 minutes.
At least 30 minutes.
Why not?
We can't waste the time. We got a lot of material to cover between now and the end of the semester.
Let's just do it on the 17th.
No.
Yes.
Tuesday, you're still willing to do a study session at your house?
Yeah, if you're interested, I figured that since we don't have class on Tuesday, it might be a good day to meet to get some studying done. And if I come up here, I'll give you 2 hours, but if we meet at my house, I don't have to travel, I'll give you 3 hours.
What time?
And I've invited my other class to come because they have a test on Wednesday when we get back.
Where you live?
I live in Stockbridge.
What time does
8
it
miles from here.
Marietta.
And I'm suggesting maybe 12 to 3,
Yeah.
noon to 3. So Tuesday,
I assume you'll give us your address.
No.
I'll send you an email with the address and the map
Thank
or
you.
directions to get there. And my phone number, you already have my phone number, so you can call when you're lost. All right? And so there's an opportunity for you if you can and want to make it. You're welcome to come. Spend a couple hours, we'll answer questions. All right? Any other issues?
So the test is on Thursday?
You ready to vote?
Yes.
All right, all in favor of Thursday the 17th?
Y'all are crazy. You just want new material. New material mess you up.
Tuesday the 22nd.
Thank you.
Wow.
You're gonna be just as prepared for Thursday.
Exactly.
I have a trig exam. Yes.
What an omen that is. All right.
Dr. Braun, I have a question.
Dr.
Yes.
Braun, can you clarify for him that it doesn't mean that there's gonna be more material on the test, it just means we're gonna move on?
It does not mean that there'll be more material on the test. We are just going to move on.
Thank you.
Is that clear enough?
Quite a few people up in here. Yeah, but you're gonna move on.
Yes.
I have an issue.
No, we're not done.
Is it okay if I post the videos on Facebook or Facebook?
What videos?
She takes videos.
Oh, I don't care.
Okay. So should I ask the class, is it okay?
Is it
Can I have
okay?
everyone's attention, please?
All right, we have a suggestion from a student.
I wanna know you're right.
Okay, I record the videos for chemistry, and we have a Facebook group. So I just want to ask if anyone has a problem with me posting them on Facebook, since some people ask questions.
They need to
Okay,
That's your Facebook.
it's the class has a group. It's a classroom Facebook group. So the recordings aren't the best, but if you don't mind, I'll post them on there.